Hello everyone, my name is Qilin. I'm from University of New South Wales. I'm giving this talk on our paper of IMWT Volume 4, Issue 1, Article 41. It is about our key generation system for body area network. Let's start with the background. In multi-variable scenarios, wearable devices may need to frequently exchange highly private sensory information. In order to protect sensitive information, legitimate devices must establish initial trusted relationship. Traditional approaches are based on pre-deployed secret. However, they are not scalable with growing number of wearable devices. In the area of band security, exploiting biometrics as shared secret is one of the most popular directions for the key generation system. Biometrics are inherently unique and accessible for wearable devices, and usually they are hard to obtain or spot for malicious devices. Currently, popular biometric choices include heartbeat, gait, etc. Though previous work demonstrated the feasibility of biometric-based key generation system, the power consumed by high-frequency accelerometer sampling is considered significant for resource-constrained wearables, while harvesting kinetic energy from human activities drawing lots of research attention. Previous studies also showed that KEH can be used as an energy-efficient alternative for accelerometers. However, due to a high level of noise inherent in KEH signal, the key generation system needs to tackle more bit mismatches. Under this background, we propose KEHkey system. KEHkey system explores the gate shape captured by KEH as a shared secret. Suppose Alice and Bob are two KEH-embedded wearable devices, one on a user. At first, Alice and Bob sample the user's gate signal independently and simultaneously. Then they quantize the samples into bit streams. Finally, Alice and Bob apply an information reconciliation approach to correct mismatch to agree on the same final key. We built 4 prototype devices by instrumenting a data logger, that is, sensing text from Texas Instruments, with a KEH, that is PPA1001 piezoelectric cantilever produced by my technology. We collect data from 24 participants. All participants wore 4 phototypes on their chest, waist, head, hands, and they were asked to walk indoor at their normal speed. Accurate time synchronization of 2 devices is needed, as even a small temporal offset can lead to numbers of mismatches. On receiving the communication request or response, 2 wearable devices synchronize their clocks by observing the next heel strike, which can be detected accurately during each step. When KEHkey attempts to collect data from users' hands or users' arms, the energy generated from the limb swing will be added to the total KEH signal, making it difficult for key pairing. It is clear that step frequency on torso is as twice as that on the arm. Therefore, we can filter out limb swing components with a bandpass filter. Figures below show the effect of the simple bandpass filter. We use a conventional two-array GAR band-based quantization method to convert gate shape into bit streams. Each sample is quantized to be 0, 1, or discarded. In symmetric key generation system, 2 legitimate parties generate their keys independently. 2 keys are usually similar but not the same. To correct mismatch, we implement state-of-the-art compressive sensing-based information reconciliation approach. In CS-based information reconciliation protocol, one pairing device transmits its compressed key via a public channel so that its pairing party can correct the mismatches based on the compressed key. Dimension of compressed key is the balancing factor of security and effectiveness. If the compressed key is too short, legitimate parties cannot correct all mismatches. If it is too long, it will leak too much information to attacker so that attacker can derive the secret. We select dimension based on collected data to ensure effectiveness and security. After tuning all parameters of our system, our results show that KEHkey can generate the same key for two legitimate devices at a speed of 12.6 bits per second. It can also reduce energy consumption by 59% compared to accelerometer-based method. To analyze the security of the key generation system, we also developed 3 typical adversarial attacks: passive eavesdropping attack, active mimicking attack, and the video side channel attack. Our results show that they can achieve 74% of beta agreement rate at the highest. As key generation systems require B for B equal key, they have 0 success rate. And that concludes our talk today. Thank you.